Hi everyone, good morning. Today we'll be speaking about Glacier V3, which is our carrier board for accelerator modules. I'm Pavan Shetty from the platform hardware team in Meta.
I'm Seibert from the mechanical engineering team.
Hello, I'm Soumya Padmanabha from hardware system team.
So today we'll be going over GPV3, which is our next generation accelerator carrier card. It holds our M.2 and dual M.2 accelerators. These are form factors that we had defined a few years back and contributed the specs to OCP. GPV3 is a PCI switch-based expansion card which connects to our existing single-socket Yosemite V3 platform. It allows us to connect additional acceleration compute to our existing one-socket servers and enable specific application workloads. So today we'll be going over mainly the platform design and how these systems plug in into how these carrier cards plug in into the YV3 and showcase the modular design philosophy we leverage from YV3. So before we get into GPV3, a little bit about Yosemite V3. This is our workhorse single socket platform that we have been deploying since 2021. It's next generation to YV2 and it plugs into our ORV2 21-inch rack. The YV3 platform has multiple configurations. You could have four 1U servers in a sled or two 2U servers with expansion cards. Or as we will discuss later, one large 4U servers with a lot of expansion cards. Within the server, there are some configurations we can run as well. We can have a shared BMC or NIC across all the servers, or you can have standalone NIC and BMC for each server based on the bandwidth required by the application. It's definitely designed with scalability and servicing in mind. Each of the servers are hot serviceable, so you can service one server without impacting the other servers in the sled. So GPV3 allows us to connect 6 dual M.2 or 12 M.2 accelerators to a YV3 platform. We have two configurations. In the original configuration, we had one carrier card plugging into one motherboard in the YV3. Motherboard in this case being Delta Lake. This configuration can support both shared NIC and dedicated NIC configuration, as I mentioned earlier. We found that there are some applications which need more accelerators to one compute node. So we have another configuration which allows us to connect two Glacier points to one head node using an intermediate switch card called Cottonwood Creek. And that's what I've shown here on the right. So this is what the PCI block diagram looks like. So we have 24 lanes from the host, from the riser connector of the motherboard. And we can expand this to 6 PCI Gen 4 dual M.2 modules and 2 UN.S SSDs to support additional storage for these applications. Since we have two ports from the host, we have two partitions on the switch. Within the switch, it allows peer-to-peer communication across all the end devices, both within a partition and across partitions. Some more details on the Glacier Point card itself. In addition to the switch, we have a microcontroller, which we call the bridge IC, to monitor the sensors and run the firmware management on the board. There's a CPLD to do power sequencing and reset control. And each of the modules have their own power sensing and power control, because we want to have very robust telemetry when we deploy these in the fleet. Since these are accelerator modules with a variety of different use cases, we also have a USB and JTAG connected on the carrier card for debug. USB enables us to access all these cards at the same time for debug that involves workloads that consume, run on multiple accelerators at the same time. So when we go into when we need to plug in additional carrier cards, two GPv3s per server, we use an intermediate switch card called Cottonwood Creek. It's very similar to GPv3, so it basically takes the uplink from the host and splits it into two GPv3s. It also has the same functionality like the GPv3, a big microcontroller for power monitoring and firmware management, and USB hub to expand debuggability into both the carrier cards. Now we'll move on to the mechanical design with Lauren.
Thanks, Pavan. So from a mechanical perspective, we have two system designs. We have a 2OU system, which I will be going through first, and a 4OU system, which is a little more complex. Regarding the 2OU system, so this chassis consists of the Delta Lake motherboard and one Glacier Point V3 board. This board is connected to the Delta Lake through a series of two PCIe riser cards, which you will see in the next slide. So as Pavan mentioned, we did design these blades with serviceability in mind. So our key components here are the M.2 modules and the E1.S drives on the Glacier Point board. So in order to access the top M.2 modules, so this is the top half, the 6 single M.2s, you can open the top cover as shown in the top right-hand corner by sliding and rotating that into the open position. In order to access the lower M.2 modules, you do need to remove the entire riser cage on the front, which is shown as in the blue chassis. This can be removed by releasing a series of two side locking mechanisms on the side of the blades. And once those are unlocked, the riser cage can easily be removed from the blade base. And at that point, the lower M.2 modules can be accessed, as well as the E1.S drive. And as you can see in the lower right, there are the two riser cards. That's where we mate to the motherboard. Regarding the 4OU system, so this one is a little more complex. So with this architecture, the Delta Lake motherboard actually connects first to the Cottonwood Creek switchboard. And from there, that switchboard connects to two Glacier Point boards, so one on the top, one on the bottom. Next slide, please. So in order to service the system, so very similar to the 2OU blade, so we have side latches here as well. There are four, in this case, two on each side, in order to remove the riser cage from the blade base. And once this riser cage is removed, as you can see, there's an air baffle and a bracket around the CPU. So in order to service the DIMM, CPU, etc., those could be removed. So regarding the riser cage itself, so in order to access the Glacier Point board, so again, keeping serviceability in mind here, we have similar side latching mechanisms that can allow both the top and lower bottom module to be removed. Mechanically speaking, these are interchangeable, so it's the same to remove one versus the other. And again here, the top M.2 modules on the top Glacier Point and the bottom on the bottom, those can be serviced without removing from the 4OU system. And one more thing I'd like to mention, if you haven't stopped by the Meta booth already, we do have both the 4OU system, which is known as Kings Canyon, as well as the 2OU system known as Glacier Point. We do have the VR models at our booth, so please do stop by. You can look at these 3D models in detail, as well as the sub-assemblies. Okay, thank you, and I'll hand it over to Soumya for the module management.
Thanks, Lauren. So once we are done with the board design and with the mechanical design, we do get early samples. We did get early samples in-house. And while we are planning for the execution of validation of these accelerator modules, in parallel, we also plan for module management when, specifically for when these are deployed at scale in data centers, hundreds of thousands of them. How do you manage these modules and make the sustaining phase much more easier, right? And for that, we do enable basic tooling. When I say tooling, it covers various aspects of these modules. How do we address the errors that we see in these modules, and like firmware management and error management, and make sure that the power closely monitor the power on these modules. When I say firmware management, it's what version does it have, the right version across these thousands of modules, and every modules have to have the same version of the firmware running on them. And so these are the kinds of areas that we focus in, basically monitor continuously and have a tool in place to monitor these modules when deployed in the data center at scale. So to support the tooling, we have the basic module telemetry enabled and in place to gather metrics like bandwidth, perf, or errors, and configuration checks. So every critical aspect, sensor data, every critical aspects of the M.2 module, accelerator modules are checked and monitored continuously in the data center. And even the errors, right? We do see the errors. What do we do with them? And they might not be errors across every single module. Handful of accelerator modules shows up different errors. So we do plan for the repair work in place at the data centers. And imagine this is at scale, not at the lab bench, or not just 100 of modules. So we need to have a repair flow in place for every kind of error that we anticipate and be able to resolve it quickly. So all this is planned way ahead in time, in parallel, while we are evaluating hardware for robustness. And one thing is, we do see the errors, right? We do see errors in these modules. Which module are we seeing errors, right? We need to plan to be able to identify these errors. Where are they? Where do we see the errors? So for that, we do have a distinct out-of-band access from BMC based on FRU and sensor addressing. We are able to identify any module in the data center that fails and track them. And if we want to access them via host, we do track them via SMBIOS or dedicated physical slot IDs, like slot ID 1 for modules, and different 6 or 12 modules in the system. So all this module management is planned ahead in time, repair flow, monitoring these errors continuously, and preparing ahead for when we see the errors, how do we address them. So these are all, and having a robust telemetry to track these data, both at module level, sometimes at a server level, and also at rack level, is part of the module management which is in place. Next slide, please. So I just wanted to share a logical block diagram to show this is what we use as reference for accelerator modules and carrier card. This pretty much covers the complexities that come with maintenance in DCs and module management, and including validation as well. So as Pavan mentioned, there are some enhancements from previous version of this design for the accelerator carrier card, and that is definitely from moving from Gen 3 to Gen 4 PCIe speed. And for that, it's also a little more complicated. As it was mentioned earlier, the switch is partitioned. When we deal with the module management and especially handling errors and sensor data, we want to be able to identify which partition of the switch are we receiving, and is the repair flow identified correctly for that. So just to show the complexity of it, it might look simple when we are dealing with one module, but trust me, when you look at thousands of servers and hundreds and thousands of these modules in data center, the planning of this module managers is very, very critical. Especially these carrier cards and accelerator modules. And this also serves as a reference for not only for module management, for accelerator, M.2 accelerators, but also for validation purpose as well. Some of the validation strategy we have implemented is, of course, based on the module that we just shared. And once we get the hardware, we want to check, we do check on the bench and on the rack level and enabling it in DC and verifying both functional features of these M.2 modules, as well as the robustness hardware, and not just from point of view of accelerator module. It also from the point of system integration as well. So when these accelerator modules are enabled in the system, we do validate the firmware validation. Does the system behave as expected when we have this kind of firmware, and is the error tracking or how does the system response is for a particular error, and also stress the accelerator with the current existing firmware. For example, run complex modules, complex models depending on the use case, of course. So we run complex models on these and stress the accelerator. And also overall system test and monitor power and critical features of these M.2 accelerator modules. That is all part of the validation as well, done very early on in the cycle. It's done in different stages, of course. Once it's a bring up stage, and then we move to the little mature stage. And we also combine with hardware and system integration validation. We also combine the testing of tooling in place. So we enable, when we do stress these modules, are the tooling in place able to monitor them right in the data center? So all this is planned well ahead of time for accelerators. And another thing is perf benchmarking, right? It's very critical. That is what we are all looking for with M.2 accelerators. And depending on the use case, we do run complex models, sometimes distributed model, which one module cannot handle, but distributed across 6 or 12 that we have on the system, and make sure the system behavior is as expected. And it's a full stack as well. We have, for accelerators especially, we have a hardware stack and a software stack sitting on top of it. So we want to make sure there is expected behavior when we run the full end-to-end validation and make sure the perf benchmarking is met. And that is definitely the whole purpose of the validation at the end of it. And what we realized from accelerators is also make sure that we are ready for the manufacturing, right? That solves half the problem. In the sense, we want to make sure that what is enabled on all the software that's enabled on the systems are what we expect to land in the DC, and drivers, compilers, and so on. And for that, we also, and another thing is also screen out the defective modules ahead of time. Never ship or totally avoid shipping a defective module to the data center. That really does save us some time. So manufacturing readiness is part of that. And the next two slides show us some of the product info and contact info where you can reach us with any further questions. Thank you. If you guys do have any questions, feel free to ask now if the time permits.
Yeah, thank you.